In this lesson, we will focus on Task 2.2 within Project 2, which involves boring machining technology and precision hole machining tools. We will delve into the boring bar system and machining accuracy. We will explore the relevant concepts and the structural characteristics of the boring bar system, analyze the factors affecting machining accuracy, and learn methods to improve machining accuracy. By comparing the rough machining of drilling with the fine machining of boring, we will appreciate the transition from approximate to precise and understand the importance of precision measurement and accurate adjustment in modern industry. Overview of the boring bar system. The boring bar system is a critical component in boring machining. Boring is a method of remachining existing holes commonly used to enhance the dimensional accuracy, shape accuracy, and surface quality of holes. As an essential tool in boring machining, the boring bar rotates under the drive of the machine tool spindle to cut the holes on the workpiece. Structurally, a boring bar typically consists of a bar body, a tool mounting section, and a connection section. The bar body is the main part of the boring bar, and it needs to have sufficient strength and rigidity to ensure that excessive deformation does not occur during the cutting process. The tool mounting section is used for installing the boring tool. Different types of boring tools can meet different machining requirements. For instance, rough boring tools are used to remove a large amount of material, while fine boring tools are used to ensure the final accuracy of the hole. The connection section is used to connect the boring bar to the machine tool spindle, enabling the transmission of power. In practical applications, the boring bar system is widely used in industries such as aerospace, automotive manufacturing, and machining. For example, in the manufacturing of aircraft engines, where high-precision holes need to be machined, the boring bar system plays a crucial role. Strength and rigidity. Strength refers to the ability of the boring bar to resist damage. During the cutting process, the boring bar is subjected to cutting forces, and if its strength is insufficient, the bar may fracture, disrupting normal machining operations. Rigidity, on the other hand, refers to the ability of the boring bar to resist deformation. When the rigidity of the boring bar is inadequate, it may bend or twist under the influence of cutting forces, resulting in a decrease in the shape and dimensional accuracy of the machined hole. For example, when machining deep holes, if the rigidity of the boring bar is insufficient, it may lead to an increase in cylindricity error of the hole. The accuracy of the boring bar includes dimensional accuracy, shape accuracy, and positional accuracy. Dimensional accuracy refers to the precision of dimensions such as the diameter and the length of the boring bar. Shape accuracy pertains to the precision of the bar's straightness and cylindricity. Positional accuracy involves the precision of the positional relationship, such as the coaxiality between the boring bar and the machine tool spindle. These accuracy indicators directly affect the precision of boring machining. Balance. When a boring bar rotates at high speed, any imbalance can generate centrifugal force, leading to vibration and noise, which affects machining accuracy and surface quality. Therefore, the boring bar needs to be balanced to ensure stability during rotation. Balancing is typically achieved by adding or removing counterweights on the boring bar. Factors affecting boring machining accuracy. Factors of the boring bar system. The rigidity of the boring bar is one of the key factors affecting machining accuracy. As mentioned earlier, insufficient rigidity can lead to deformation of the boring bar, thereby affecting the accuracy of the hole. Additionally, the manufacturing accuracy of the boring bar also impacts machining accuracy. If the dimensional accuracy, shape accuracy, and positional accuracy of the boring bar do not meet the required standards, the accuracy of the machined hole will also be affected. The selection and installation of the tool also affect the machining accuracy. Different types of tools are suitable for different materials and machining requirements. If the tool is improperly selected, it may result in excessive cutting forces and poor surface quality. The installation accuracy of the tool is also crucial. If the tool is not installed accurately, it can lead to changes in the position and angle of the cutting edge, affecting the dimensional and shape accuracy of the hole. Factors of the workpiece. The material properties of the workpiece affect machining accuracy. Different materials have varying hardness, toughness, and cutting performance. For example, materials with higher hardness require greater cutting forces during machining, which can easily lead to deformation of the boring bar. On the other hand, materials with better toughness tend to produce built-up edges during cutting, affecting surface quality. The structure and shape of the workpiece also affect machining accuracy. If the workpiece has a complex structure, it is prone to deformation during clamping and machining, which can affect the accuracy of the hole. For instance, if excessive clamping force is applied to thin-walled workpieces, it may cause deformation, leading to increased roundness and cylindricity errors in the machined hole. Factors of the machining process. The selection of cutting parameters has a significant impact on machining accuracy. Cutting parameters include cutting speed, feed rate, and cutting depth. Excessive cutting speed can lead to increased tool wear, affecting machining accuracy and surface quality. An overly large feed rate can increase cutting forces, causing deformation of the boring bar and affecting the accuracy of the hole. Similarly, an excessive cutting depth can also increase cutting forces and may induce vibrations, impacting machining quality. The machining sequence also affects machining accuracy. A reasonable machining sequence can reduce deformation and error accumulation during the process. For example, when machining multiple holes, rough machining should be performed first, followed by finish machining to ensure the final accuracy of the holes. Methods to improve boring machining accuracy. Optimize the boring bar system. Selecting appropriate materials and structures for the boring bar can enhance its strength and rigidity. For instance, using high-strength alloy steel to manufacture the boring bar can increase its strength. Employing a hollow structure for the boring bar can reduce weight while maintaining a certain level of strength, thereby improving its dynamic performance. Performing dynamic balancing on the boring bar can reduce vibration and noise, thereby improving machining accuracy. Balancing can be achieved using specialized balancing equipment, which adjusts the balance by adding or removing counterweights at appropriate positions based on the amount of imbalance in the boring bar, bringing it to a balanced state. Select tools and cutting parameters reasonably. Choose appropriate tools based on the material of the workpiece and machining requirements. For example, for materials with higher hardness, carbide tools can be selected. For machining with high surface quality requirements, coated tools can be chosen. Reasonably selecting cutting parameters can reduce cutting forces and minimize deformation of the boring bar. Generally, during rough machining, a larger cutting depth and feed rate can be chosen to improve machining efficiency. During finish machining, a smaller cutting depth and feed rate should be selected to ensure machining accuracy and surface quality. Adopt advanced machining processes and technologies. Utilizing CNC boring can enhance machining accuracy and production efficiency. CNC boring machines can precisely control the movement path of the boring bar and cutting parameters through programming, reducing the influence of human factors. Employing error compensation technology allows for real-time monitoring and compensation of errors during the machining process. For example, by installing displacement sensors to monitor the deformation of the boring bar, the control system can then adjust the cutting parameters or the position of the tool to compensate for errors and improve machining accuracy. Compared to drilling, drilling is a rough machining method primarily used to create holes in solid materials with relatively low precision, often only meeting approximate size requirements. Boring, on the other hand, is a finishing process that enables the transition from approximate to precise. This transition from rough machining to finished machining highlights the central role of precise measurement and accurate adjustment in modern industry. In the boring process, it is essential to precisely measure and adjust the dimensions of the boring bar, the position of the tool, and the cutting parameters to ensure that the machined holes meet design specifications. This requires us to cultivate an engineering mindset that values precision and respects scientific principles. In practical work, we should not be content with approximate results, but should strive for precise values and perfect quality. Taking the machining of valve core holes as an example, the valve body contains multiple high-precision holes, and the accuracy of these holes directly affects the performance and reliability of the hydraulic valve. Boring is typically used for machining these holes. First, select an appropriate boring bar system. Choose a boring bar with sufficient strength and rigidity based on the size of the hole and the machining requirements, and install the suitable tool. Then, use a CNC boring machine to precisely control the movement path of the boring bar and the cutting parameters. During the machining process, employ error compensation technology to monitor and compensate for the deformation of the boring bar and tool wear in real time, ensuring the accuracy of the holes. With this machining process, we can control the dimensional accuracy of the holes in the engine block within a very narrow range and achieve a high level of surface roughness, thereby enhancing the engine's performance and reliability. In this lesson, we primarily explored the relationship between boring bar systems and machining accuracy. We began with an overview of boring bar systems, including their structure and applications. Next, we discussed the performance requirements of boring bar systems, such as strength, rigidity, accuracy, and balance. We then analyzed the factors affecting the accuracy of boring machining, including the boring bar system, the workpiece, and the machining process. Finally, we learned the methods to improve boring machining accuracy, such as optimizing the boring bar system, selecting appropriate tools and cutting parameters, and adopting advanced machining processes and technologies. Additionally, by comparing the rough machining of drilling with the finished machining of boring, we experienced the transition from approximate to precise, emphasizing the importance of precise measurement and accurate adjustment in modern industry. I hope everyone can cultivate an engineering mindset that values precision and respects scientific principles.